Hello, Professor and fellow students. I'm Nicholas DeStefano, the Project Manager for Northern Consulting, Inc. It is my pleasure to introduce our team: Wenhan Lo, the Project Leader, Raymond Jarlego, the Project Specialist, Munir Jobin, the Project Coordinator, and Alexander Mutton, our Documentations Manager. This is the outline for our Term 1 summary. In Term 1, the team completed preliminary assessment for sediment remediation, with the main objective being the design of a treatment system for contaminated sediments on Villers Island, and ultimately prepare the site for further development. The team also focused on soil remediation, in which the main objective was the remediation of the contaminated soil at Cherry Street South Bridge location to prepare the site for construction and reduce environmental impacts on the project. Furthermore, the water mains and sewer mains design were also evaluated in the preliminary phase, in which NCI's primary goal is to provide the island with water and sanitary services that would accommodate the needs and requirements of the residents and communities. NCI was also responsible for the preliminary assessment and design for the Cherry Street South Bridge that was proposed to connect the island with the mainland. My colleague Munir will now further elaborate on highlights of the Cherry Street South Bridge design and their significance towards the project.
Thank you, Nicholas. In the primary phase of the design of the Cherry Street Bridge, the primary objective of the design was to accommodate the transportation needs and requirements for Villers Island that would meet the design requirements for the flood control and aesthetic appeal for the Portland Naturalization Project. Based on the analysis of 3 different alternatives, NCI was able to provide a bridge design that we believe would satisfy the transportation requirements outlined through the scope of the project. The alternative selected would consist of a beam bridge with 3 spans, the outer spans being 35 meters long and the middle spans being 50 meters long as shown in the figure. Furthermore, the bridge itself would accommodate a pedestrian walkway along with a dedicated cycle path on both driving directions. The bridge will also accommodate 2-way traffic that is designed for bus route accessibility, all of which was accomplished using a pre-stressed concrete girder design similar to that shown in the figure to the right. From the analysis completed on the bridge design and the information obtained during the preliminary research, NCI was able to relate some of the findings to the continued work in the second phase of the project, in which the grading and the elevation map obtained for the bridge design will further be used for the design of the water main and the sewer network, along with having a better understanding of the connection points of existing water service infrastructures on Cherry Street and the mainland that meets the bridge. The bridge design also assisted in understanding the soil remediation requirements for the second phase of the design, in which the footing and the foundation of the bridge would influence the volume of the soil to be remediated. This information was therefore used to assist in the continuation of work in the second phase of the design. Nicholas will now discuss the elements of the second phase and the work completed towards sediment remediation at Villers Island.
Thank you, Munir. In Term 2, after thoroughly assessing all the feasible options, we completed detailed designs for sediment and soil remediation and water and sewer mains, while including heat recovery technology. Annually, the Don River dumps 30,000 cubic meters of contaminated sediment into the Keating Channel, which must be dredged to prevent flooding in surrounding areas. We were entrusted to find a sustainable method to manage the sediment. We decided on 2 remediation options. One was in-pile thermal absorption with phytotechnology, and the other was plasma vitrification technology. All considered, we decided on plasma vitrification since it destroys organic contaminants while encasing toxic metals in a glass-like rock. It is the most sustainable choice since the waste is converted into new products such as shingles, road aggregate, and even floor tile. The process is very affordable at $130 per cubic meter of sediment remediated. We had to locate a suitable site and design a remediation facility that could manage the volume of sediment. First, we designed the plasma furnace. Reaching temperatures up to 4,000 degrees Celsius, the furnace had to be designed with an outer skin strong enough to contain the molten slag and withstand the high temperatures. We chose a tungsten nickel iron alloy outer skin with a lying tantalum hafnium carbide refractory brick. The proposed site is at 2095 Codling Crescent at Highway 407 and 427. The site consists of 4 large exterior concrete bins, able to store half the dredged annual sediment. Dump trucks enter the yard at Albion Road and dump their sediments in the bins. The sediment is then loaded into the hopper located at the rear of the building, which is connected to a vacuum tube that transports the sediment to the second level of the facility. The sediment is fed onto one of 2 rotary dewatering presses that reduce the sediment volume to be treated by approximately 50%. The sediment is then sent to one of two storage cycles, where it is gravitationally fed in the plasma furnaces. For safety, the furnaces are contained in a sunken area in the event the outer skin is breached. The molten slag travels in pipes within the concrete floor to the crusher, where it is quenched with jets of water and crushed. The crushed slag is dropped into the disposal bins, waiting to be hauled away and sold. This is a cross-section of the plants. Now to Alex for soil remediation.
Great, thank you, Nicholas. Now for soil remediation, Northern Consulting was tasked with performing a Phase 1 site assessment and reviewing a Phase 2 site assessment work at the Cherry Street South Bridge site. This first-term review allowed Northern Consulting to determine the soil volume of approximately 450,000 meters cubed being contaminated with petroleum hydrocarbons, polychlorinated biphenyls, inorganics, metals, volatile organic chemicals, and polycyclic aromatic hydrocarbons, all that need to be removed from the site before the bridge construction can begin. Once the contaminants and their concentrations were determined, Northern Consulting Inc. was able to determine 3 design alternatives that could be applied to the site. These alternatives included excavation and landfilling, off-site soil washing and bioremediation, and finally, a soil recycling facility on the Portlands. With the soil recycling facility on the Portlands having low greenhouse gas emissions due to minimal equipment travel, as well as reusability of recycled soils, this alternative is the best design that provides the most effective and sustainable design for the client. The soil recycling facility will operate with a soil washing process combined with thermal desorption and bioremediation. Shown in this image, NCI has proposed a site for the soil washing equipment, along with a soil pile zone that will host the thermal desorption and bioremediation. The equipment will be comprised of numerous soil screens, spiral classifiers, attrition scrubbers, and hydrocyclones, to name a few. To determine the amount of soil processed through the soil washing phase, NCI has developed a soil mass balance for the different equipment throughout the process. This is shown in the example on the slide, where on the left we have the inflow of both soil and water for the equipment shown, as well as on the right we have the outflow from the process of both soil and water. Ultimately, the soil mass balance, we are able to determine 10% of the original soil will be transferred to the soil pile, which NCI has created a design for. Shown in this design drawing, NCI has created a soil pile that has a 60 mil HDPE liner on the bottom of the pile. Contaminants do not leach off the site. As well, a 20 mil HDPE liner that protects the contaminants in the pile from water and wind erosion. In the soil pile, we can see 5 aeration pipelines that will be used for both bioremediation and thermal desorption phases, along with the thermal piping for the desorption phase. The soil pile will be equipped with 2 monitoring points to consistently monitor the soil pile for its productivity. Now I'll pass it to Wenhan to talk about water main work for the project.
Thank you, Alex. So NCI was also projected to design a water distribution system on Villers Island that can deliver potable water for domestic consumption while having a sufficient capacity at all times so that we can deliver adequate quantities of water at adequate pressures for firefighting purposes if necessary. In our term 1 work for the water mains, we first determined the water demand. So NCI sectioned off Villers Island into blocks of different land uses such as catalytic, community centers, residential, and commercial buildings. And from that collected data, using population and total floor space, we were able to come up with the water demands of liters per day on Villers Island. Also from term 1, NCI was able to produce a basic working water main layout, which was then worked upon through term 2. So from the term 1 data, we were able to come up with the water demand pattern for each block to determine the peak hours of water demand to ensure our water main system can handle these scenarios. As water demands aren't always the same throughout the day, it is important for us to account for these demands as they usually go up and down during, let's say, lunch hours or even evenings through 6 to 8 p.m., as residents consume the most water during these times. With the help of data from the 2019 Toronto Sewer and Water Main Manual, we were able to come up with an accurate representation for these water patterns for mostly commercial and residential areas. These were then implemented into the EPA net, which I will talk about later. For now, I'm going to be talking about the fire hydrants that were also implemented into the system. The number of hydrants were spaced and determined through the guidelines, and the fire flows were calculated for each block on the island. This tells us how much water the system must distribute as a certain area if a fire were to occur. As the hydrants were placed, we tested it through 2 scenarios to see if the water main system can handle the hydrants. One being on the shown on the left, in the center of the system. In this block, it also required the most water if a fire were to occur, which our system was successful in handling while running the simulation. Seen on the right, another scenario, which was where the hydrant was the furthest away from the source of water, as this will show that our system can properly distribute high amounts of water to the furthest point from the source. And this was also successful when running the simulation. This proved that our system was successful in the implementation of hydrants. So to test all these scenarios and water pressures, NCI used a tool called EPANet, which helped us lay out a water main network with features that helped us determine if our network would be stable through these daily water demands. We were able to input a lot of variables such as elevation, pipe sizes, roughnesses, and friction factors, which helped us get a closer look as to a real-life simulation. Through our simulation and tests, NCI can confidently say that a fully optimized water main system for the Villars Island was produced, following the Toronto guidelines and standards, with a system that can sustain water demands at peak hours with or without fire hydrants. Now I'm going to be passing on to Raymond, who will be talking about the sewer network design.
Thank you, Wenhan. In this section, I will be explaining the methodology of sizing pipes and making a comparison between alternative designs. To give you a closer look, this is the sewer alignment, with the background being a scaled grading plan and blue arrows representing the direction of which the ground slopes toward. To size pipes, the following inputs are used: Manning's coefficient, wastewater flows to each manhole estimated in term 1 based on projected population densities, pipe lengths, and the assumed pipe diameters and slopes. The City of Toronto allows for pipe flow velocities to be within 0.6 and 3 meters per second, but our design aims to minimize velocity to reduce the pipe material degradation over time. All pipes will be designed to flow at 80% full, with adherence to design guidelines to minimize pipe slopes by maximizing the hydraulic radius of each pipe. The process of sizing pipes is iterative. After meeting flow velocity requirements, the flow capacity of the pipe is calculated and compared with the flow received by the manhole where the beginning of the pipe is connected. If the flow capacity is less than the flow received by the manhole, either the pipe diameter or pipe slope will be increased, which also increases the pipe velocity service flows from the manhole. Here is a sample of the outputs. Now, in some cases, you'll notice that the velocity is higher than 0.6 meters per second to accommodate the requirements from the guidelines. As an example, pipe slopes have to be at 1% for the initial branches of a sewer network and 2% for pipe lengths equal to or less than 40 meters. In total, we have explored 12 sewer design alternatives, but we will be closely looking into alternatives 3 and 4. A quick note is that all pipes used are concrete except for the 254 millimeter pipe, which are made of PVC. Here are construction detail samples. The drawing on the left represents the pipe cross-section in adherence to Toronto standard sewer specifications, and the one on the right represents the cross-section of the main line from Network B. To choose a final design, cost, complexity, and sustainability will be the parameters of comparison. Based on a decision matrix, we have decided to select alternative 3 above all others, though alternative 4 comes closely behind in second place. I'll now hand it off to Munir to discuss the heat recycling technology implemented in our design.
Thank you, Raymond. At NCI, we strive for sustainability in our design and innovation in our engineering work. Hence, we have undertaken efforts to implement a heat recycling system as part of our design to the sewer network for the district of Villars Island. A heat recycling system allows for the recovery and potential savings of energy in the form of heat. Heat is continuously lost in wastewater that is discharged from buildings and residential units that have used energy to heat the water for personal and household related use. With the implementation of a heat recycling system, we aim to capture the wasted heat and return that energy to the district for various uses, such as water and space heating. To assess the feasibility of the design, we perform a preliminary assessment of the sewer network and the potential energy recovery of the system. The heat recycling system was proposed on sewer network A at the discharge point of the sewer network at Cherry Street Bridge, as shown in the figure below. The following are the results obtained for the analysis of alternative number 3 and alternative number 4. The primary differences between both alternatives are based on the choice of pipe material and pipe dimensions, in which alternative number 3 is designed with concrete piping at an average inside diameter of 300 millimeters throughout the entire network. Alternative number 4 is designed with PVC piping at an average inside diameter of 254 millimeters. Based on these differences, the potential energy recovery of each alternative varies, however, only slightly. The difference in the energy recovery is based on the heat losses that occur during the transportation of the wastewater in the piping system, which is primarily influenced by the material of choice and the sizing. Based on this information, the energy recovery of alternative number 3 was found to be 450,000 kilowatt hour per year, with a potential cost recovery of $55,000 per year, whereas alternative number 4 was found to have an energy recovery of 420,000 kilowatt hour per year with a potential cost recovery of $53,000 per year. Therefore, NCI concluded that the heat recovery system would be feasible for both alternatives and material choices, with concrete piping material having a potentially better rate of recovery. With that being said, this brings us to the end of our presentation today. NCI and our design team would like to take this time to thank you for listening, and a special thanks to the advisors and instructors who made this project possible. If you have any questions and concerns regarding this presentation or other elements of the project, feel free to reach out to the design team for further clarification. Thank you.